Hello everyone, welcome back. I'm Dr. Yang Fu Guo, and today we are going to explore the embedded C again. And let's just do a brief review. So last week we talked about microcontroller. Microcontroller in CM510 is 80 Mega 2651. And we also talked about the key spec of this microcontroller as well as the pinout. And I mentioned how to download the program that we write in embedded C to the microcontroller. And I gave some examples: blinking LED, button, serial communication, buzzer, and mic. And today I'm going to give you more examples. These four: the IR sensor, reading, writing, Dynamixel, synchronized writing, and RC100 and ZigBee. So let's start from this IR sensor example. The first thing you have to know is that most of the sensors that we have, they are analog sensors. In a sense, they give you some analog signal. Okay, but the microcontroller we have is a digital microcontroller. It can only process signal that is in digital format. So in a sense, we have to do a analog to digital conversion. So let's see what's a digital signal and what's an analog signal. So for most of signal that we are dealing, they are time series signal. In a sense, the amplitude of the signal varies in time. So the x-axis represents the time and y-axis represents the amplitude of the signal, the amplitude. Okay? And an analog signal is a continuous signal. Okay? And they go up or down along changes in time, like this. Okay, so we write here, this is analog. Okay, and what's a digital signal? Digital signals are basically discrete signal. So we sample the analog signal once a while, and the cross mark represents the sample data point. So they are discrete signal, like this. And these are digital signal. Okay. And how do we do the analog to digital conversion? And we have some on-chip ADC that is embedded in a microcontroller. Okay, so all we have to do is to connect the wire properly to the microcontroller and enable the function. And here on the right side, we see a picture of a sensor connection port. And we have several of these. They are labeled with Roman number 1, 2, 3, 4, 5, and 6. Okay, we have 6 of these sensor connection ports. And each port has 5 pins. Okay. And the functions are like this. So the first pin is the sensor on-off control. Okay. And these sensor on-off control are connected to port A2 to port A7. Okay, so we have 6 of them, and each of them corresponds to one sensor connection port. Okay, and pin 2 and pin 4 basically are the power supply to the sensor. So pin 2 supply 5 volts, and pin 4 is ground. Okay, so we have like a battery here. Connect to pin 2 and pin 4. Okay, so these two are power supply. And pin 3 is the signal that we read from the sensor. Okay, so we read this signal and use the on-chip analog to digital conversion to convert the signal into a digital signal. And pin 5 is not used. Okay, I will introduce some key specs of the ADC so you can know how to set it up appropriately. So most important spec of the ADCs are, first is the range of your signal and also the resolution of the ADC as well as the sampling frequency. Okay, these three. So the range is the input range. Okay, here in our example, because we supply 5 volts here to the ADC, to the sensor. So the maximum output from the sensor is 5 volt. Okay, and the minimum is 0. Okay, so you give a power to the sensor that is less than 5 volt. So the sensor shouldn't give you any signal that exceeds 5, right? And then second is the resolution. Okay, so what's the resolution of the microcontroller? It's a 10-bit ADC. Okay, so what does that mean? This resolution determines the quantization interval. So with this 10-bit, that means every data that is sampled and stored with a number, a 10-bit number. Okay, so the more bits you have, the finer you can quantize this range into many small intervals. Okay, so what's the quantization interval of this 10-bit? You can quantization interval. You can calculate by using the maximum range minus the minimum range and divide it by 2 to the 10. Okay, and this is your quantization interval, and the unit is in volt. Okay, and this is fixed. Like for microcontroller that we have, this 10-bit is fixed. Okay, but this tells you what your signal reading should be. Like, because it is 10-bit, your signal reading should always between 2 to the 10 minus 1 and should larger than 0, right? So 2 to the 10 is 1024 and minus 1 is 1023. Right, so your signal reading should always between 0 and 1023. Okay, and then for the sampling, this is the one that we can determine, and we have set this up appropriately. So what is sampling? That basically is how fast you want to sample your analog signal. So the arrow in the bottom represents the sample instant, and we can sample finer, sample faster or sample slower. It all depends on how you want to set up the ADC. Okay, and as I said, in order to use the ADC conversion, we have to control it. Okay, so how do we control the microcontroller? If you remember from the last lecture, we need to use register to control the function of a microcontroller. Okay, and the register to control the ADC function is called ADC control and status register A. So they are more registers, but this is the most important one, and we are going to talk this one for now. Okay, so ADC SRA. It's not hard to remember. Okay, and it is an 8-bit microcontroller. 8-bit register. Okay, 8-bit register. Okay, and each bit has its own function. Okay, so let's see the function here. Okay, the function that we will use first is the ADEN, the ADC enable. So in this bit, you can write 1 into it. So if it is 1, that means the ADC is on, or say it is enabled in the ready mode. Okay. And if you write 0 into it, then it is off. So definitely, if we want to use the ADC, what do? We write 1 in this bit. Okay. And next is the ADPSN. Okay, this is the ADC speed control. Okay, and N means from 0 to 2. Okay, so there are 3 bits actually. And the speed of the ADC, well, depends on the clock speed and also the division factor. Okay, the clock speed is fixed. It is 16 megahertz. Okay, and the division factor depends on this ADPSN. Okay, and this table shows the choice that we have. Okay, so let's say if we want a division factor that is 64, we write 1 into ADPS2 here. We write 1 into the ADPS1 and 0 into the ADPS0. Okay, 1, 1, 0. Okay, that's how we control this. And if we want to start the ADC conversion, here we write 1 into this ADSC bit. Okay, and it's right here. Okay, so we write 1 into it, and it starts to convert. Okay, and how do we know if the ADC conversion is done? So it takes a while, a few steps for the ADC to work out and figure out, okay, what's the analog number, what's the analog signal is. Okay, and if your ADC is done, this bit ADIF, there will be 1. Okay, and if it is not working, okay, or it is still working, then this bit is 0. Okay, it is right here. Okay, so that means actually these 3 registers, this one ADEN, ADPSN, ADSC, these bits, they are more like the control bits. And this bit, ADIF, is more like a status bit. Okay, it tells you the status of the ADC. Okay, so they have different function. So let's see this example. We want to change the bits in register ADC SRA in order to first enable the ADC, second set speed to clock divided by 64. So what do we do with that? Now to enable the ADC, you have to write 1 in bit 7. Okay? In order to set the speed to clock divided by 64, we write 1, 1, 0 here. Okay? So how do you write the program? How do you write C code? And the name of the register is A, D, C, S, R, A. Okay? And with that, it equal to, if it is a binary number, we write 0B, so it's a binary. And binary is easy. We know first bit is 1. Okay, and we have 0 in the following 4 bits. And we have 1, 1, 0 here. And don't forget your semicolon. Okay? So that's what your C code will look like in order to control these two. Okay, enable ADC and set speed. Okay, and what do we write in hex? So we convert this into hex. So remember, in hex number, 4 binary bits is represented by 1 hex number. Okay, so what is this in hex? Okay, so let's count the decimal number first. So the decimal number will be 8, right? 1 is 2 to the 3. Okay, so it's 8. And the decimal number of this binary number is what? This is 2 to the 3, 2 to the 2, 2 to the 1, and 2 to the 0, right? So this is 2 to the 2 plus 2 to the 1. There will be 4 plus 2, and this will be 6, right? So actually in hex, we write A, D, C, S, R, A is equal to, hex is 0H, and 8, 6. Okay? And you can always do this. But in a program, you will see this a lot. Like most of the time, we write this. ADC SRA is equal to 1 double arrow A, D, E, N. Okay. And da, da, da. Okay. So what is this? This ADEN is in the header file. Okay. It is equal to 7 actually. This is equal to 7. So this is shifting 1 to the left by 7 bits. Remember, this double arrow is shift to left bitwise. Okay? So your original binary number, if it is 1, it reads like 0B 0 0 0 0 0 0 0 1, right? And you shift that 1 to left for 7 bits. That will be 0B 1 0 0 0 0 0 0 0, right? You shift this to left for 7 bits, okay? And this is equal to what? You write 1 into the ADEN over here, right? You write 1 here, okay? So you'll see this a lot in the program because you can't always remember like what bit the ADEN is, but you remember this name, ADEN, okay? And you remember this name, ACSRA. So you can easily write a code like this, but not a code like this, or not a code like this, okay? And I will show you the code very soon. So now we learned how to control the ADC, but we still need a startup procedure in order to use the ADC. And here it is. Okay. So the first thing you have to do is to turn on the sensor that is connected to the ADC. connected to the microcontroller. So we know that port A from pin A2 to A7, they are used to turn on or turn off the sensors. Okay. So first we have to make port A to a output port. Okay. So how do we do that? We write 1 in the register DDR8. Remember that 1 is used to make a port output, and 0 is used to make a port input, right? And then for the sensor connected to the microcontroller, we write 0 to that port to turn on the sensor. Okay, so write 0, we turn them on. Okay, and next, the sensor ports, each of them is physically connected to a multiplexer. Okay, and then multiplexer connected to the ADC converter. Okay, it is somewhere here to the ADC converter. Okay, so we have to use the multiplexer to choose the pin that we are going to use. Okay, so for example, if we want to use ADC1, okay, we have to write ADC port 1 to the AD MUX. Okay, and then next we set appropriate ADC speed, and I've shown this, and we enable ADC. I've shown that, and then we need a short delay for rising sensor signal. Okay, it takes some time for the ADC to convert signal. Okay, and also for the sensor to start working. Okay, so we give a short delay there. And then we clear ADC interrupt flag. We clear it, so it will start to convert. Okay, and it is very special. If we want to clear this ADC interrupt flag, that is the bit ADIF, we have to write 1 to it. It is 1 when ADC conversion is done. Okay, but in order to clear it, we also write 1 into it. So remember this. Okay, and then next we start ADC conversion by what? Write 1 into the ADSC start conversion. Okay, and then we wait until ADC is complete. So how do we know that ADC is complete? We check this ADIF, right, to see if it is 1. So if it is 1, that means the conversion is done. And then after using, after the signal, after the ADC is done, then we disable ADC. We actually disable the sensor. So we write 1 into this port A, then we disable the sensor. Okay, so what if you need to use the sensor continuously? That's easy. You just put a while here. Right, and it will keep working and keep converting the signal into the digital signal. Okay, so let me show you the program now. So let's start the Eclipse. Now this is the program for the IR sensor. Okay, and in the beginning still that we need to include the header files. And here we define the ADC port. So we have 6 ADC ports, and their corresponding number is the name here. Okay, so ADC port 1, the number is 1. Okay, and here in the main program, first thing we have to do is to make port A as a output port, that is the 9. And we also have to turn off all the sensors that is connected to CM510. And because we are going to show the result of the sensor reading on screen. Okay, so we initial the serial communication. Okay, and we also have to initial the interrupt. Okay, and here is the program that I just talked about. Okay, so in order to select appropriate speed and in order to enable ADC, we usually write program like this. It will be much easier for you to memorize the code like this. Okay, and here we choose the ADC port through the multiplexer. Okay, and then next, here we clear the ADC interrupt flag by writing 1 into that bit. Okay, and after that, we start conversion. Okay, and we wait until what? Until that bit is 1. Okay, it is 0 when it is converting, or when it is not working. Okay, but when it turns into 1, that means the conversion is done, and we can read that data that is in ADC and show that on the screen. And basically, this is what the program do. Okay, so let's download the program to the microcontroller and to see how it works. Now let's open the Robotis and use its terminal function. Okay, let's connect to the robot and download that program. So remember how we do that? You press the pound key on screen and press that red button. Okay, and type enter, type hello, and choose the file we want to transmit. Okay, the file is ir.hex. Okay, and type go. You'll start converting. Okay, and now for this example, the reading is from the front IR sensor on the smart car. Okay, so front sensor is right there. See, it's flashing. Okay, and so when my hand gets close to the sensor, the reading goes up, and when I goes away, maybe you can see this easier in this way. Okay, so my hand is here. Okay, when my hand is closer, the reading goes up. When I keep my hands away, the reading goes down. Okay, and this is how it works. And let's move to the next example. Reading, writing, Dynamixel. And in this example, I'm going to show you how to control a Dynamixel device, basically an AX12. So in order to control the Dynamixel device, we need to know how they works. So let's say we have a Dynamixel actuator over here. It's a motor, X12, okay, and there is a shaft. And we want to control the shaft to rotate it to a specific position. What do? We use our CM510 as our central controller here. To tell this X12, where should you rotate that motor to? Okay, and the AX12 do that. That actuator is there is actually a controller inside this X12, and it can regulate the motor position for you. Okay, so our central controller only tells an actuator what position I want you to rotate to. So in that case, we can have many X12, okay, many of them. So all you want to do is to send a command and tells it what position I want, and it will do the job. Okay, and this is called a hierarchical control. Okay, so basically we have local controller like the AX12 that's doing the local regulation, and we have a central controller that is the CM510 that gives command to local controller. Okay, and now in the example, we want to rotate one X12 from position 10 to 200 back and forth, and also display the current position on PC screen. Okay, so on each X12 there is a control table, and X12 will regulate itself based on the numbers in this control table. So how do we control X12? Basically, we change the value in this table. So for example, if we want to move the motor shaft to a specific position, we change the value in go position, the low byte, and high byte. Okay? So in that case, we need to know where this go position is. So they are at address 30, that's the low byte address, and address 31, that's the high byte address. Okay? So with this table, you can control the actuator itself. So what option we have? We have the angle limit, the counterclockwise, and the clockwise. These two. And each is a word. Okay? It has a low byte and has a high byte. And we also have an address that we can know if the motor is moving or not. Address 46 over here. And here are the functions to access the AX12 control table. So first, because the CM510 communicate with the AX12 through the UART channel, so we have to initialize it. So here are the functions. Here is the function from Bioloid to do the UART initialization. And here are the functions for table value reading, and here are functions for table value writing. So for writing, actually we have two functions. One is to write a bit at one time, and the other is to write a word at one time. So what's their difference? So remember, for the Bioloid robot, one word is equal to 2 bytes. And the byte has to be adjacent bytes. Okay, so we have one low byte and plus one high byte. That is one word. Okay, and what information do you have to give to those functions? We have to tell what model we want to write the data. Okay, so this ID is the Dynamixel ID. And we have to tell what address we want to write into data. And that's the memory address. And what value we want to write into that address. Okay, basically to give those three properties. Now, Let's see how the program works. Let's check the program in the Eclipse. So this example is in the folder read write. We click it on it and double click on main. So here is the program itself. So still in the very beginning we include the header files, and then in this table we define the AX12 control table address. So remember that for the goal position, for low byte, the address is 30 and high byte address is 31. For the present position, low byte, the address is 36, high byte is 37. And we have a byte that is used to check if the motor is still moving. Okay, address is 46. And here's the main program. Now, remember in this example, we want to change the position of the motor from 10 to 1000 back and forth. Okay, so here are the two goal positions. Okay, two positions. And we want to switch from one to the another. And if we reach this one, then we switch it back to this. Okay, and we use an index here. Okay, to remember what's the current goal position. Okay, and here in this section, we initialize the communication. So this is the communication to the PC, and this is the communication to the Dynamixel. Okay, and we also have to enable the interrupt. Okay, and now these two lines change the angle limit. Remember that for X12, there are two modes, the joint mode and wheel mode. So now in the example, we should run the motor in the joint mode. So this is to give the appropriate angle limit. So for the clockwise, the angle limit is 0, and for the counterclockwise, the angle limit is 1023. Okay. Okay, and this is basically the motor rotation. Okay, in this section. Okay, so what does it do? So first, we check if the moving is down or not. Okay, by this line. Okay, and if the communication with the Dynamixel is successful, then we do the following. Okay, so if it is not moving, that means you reach a goal position. Okay, now if the goal position is 10, so index is equal to 0. That means, okay, your goal position is 10 here, actually. 10 here. Okay, now if it is 10, you switch it to 1000 here. Okay, otherwise, if it is 1000, you switch back it to 10. Okay, so this is doing that. Okay, and you write that goal position into the Dynamixel. Okay, that is in this line. Okay, then after that, you read the present position from Dynamixel. Okay, and you also write the goal position from Dynamixel, and you show those two numbers on the screen. Okay, so this is basically what the program is doing. Okay, so and now let me show you how this works. Let's download the program to the microcontroller. And remember, we hold Alt key on your PC keyboard while press this red button. Okay, and type hello and choose file to download. That would be rewrite.hex, this one. Okay, after the downloading, type go. Okay, as you can see on the screen, one of the smart cog wheels start to go back and forth. Okay, and on screen you can see the wheel position. So the first column is the go position, and the second column is the current position. Okay, you see the go position, switch from 10 to 1000, and switch back. Okay, and current position could be very close to the go position. So this is this example. Let's move to the next example. So in this example, I'm going to briefly discuss how the control is done. Okay, so we go into the low level of the Dynamixel control. Okay, so we know that the communication between CM510 and Dynamixel X12 is through UART, and this is half duplex communication. Okay, so what do we do here? Basically, for the main controller, I can send out instruction package. This package contains command to the device, and also the device will report back what happened. Okay, so the command can be, for example, to change the go position. Okay, and the status will tell you, okay, if there's any error. Okay, and or the command can be read the current position. Okay, and the status packet will be the data of the current position. Okay, so this is a half duplex communication. So what is in an instruction packet? Okay, and this is one of the instruction packets. So these are basically, remember, those are some digital signal, 0, 1 signal, okay? And in the signal, in an instruction packet, there is a header, 0xFF, two of them, okay? And then there's an ID number, the Dynamixel ID, the unit you want to control, okay? And also you have to tell how long this instruction packet is, that is the length. Okay, and what instruction you want to give. Okay, it can be read, it can be a change value in the control table, things like that. And the parameters, that includes what address you want to change the value and what value you want to write into that address. That's are put in the parameters. And there's also a checksum in order to make sure that this packet is correct. And all of these are actually done by this Dynamixel write word for you already. So if you use high level function, you don't have to worry anything about this. So this is just the explanation of the packet in case that you need. And here are the instructions that are available to us. So what we have here is we have pin function. That can be used to check if a device is online. And we can read or write data into the X12. And we have some other functions that we can use. And here's a special one, synchronized write. So in the previous example, we control one device at a time. And this can be a problem if we have several devices that is connected to the CM510. So what we can do is to write the value into devices at one time, and that is called a synchronized write. And in one of the example, we will use this function. Here are some functions from Bioloid to help us to define the instruction packet. Okay, so for the instruction packet, we have to define ID. So there's a function, packet ID, that is used to define the ID here. And the packet length, define the length here. The packet instruction, define the instruction here. And the parameter, define the parameter here. Okay, so for the parameter, you can have more than one, right? So you have to define what parameter it is. Okay, it can be parameter 1, 2, 3 to the end, and their corresponding value here. Okay, and after you define all of these, you use this function packet to create the instruction packet. I've talked about instruction packet. Now we are going to talk about status packet. So the status packet provides information regarding the X12. And one important function of the status packet is this error message. Okay, so in the status packet, there is an error element. Okay, over here. Okay, and if it's actually a byte, and if any bit in that byte is 1, that means there's an error. So this table shows the corresponding error. Every time when there is a status packet coming in, you can go check if this byte there's any bit that is 1, and if there is, come back to this table and you will see what the problem is. The next example is Dynamixel synchronized writing. And here I will briefly explain what it is doing here, so you can understand the example when you read the C code. And here the task is to control 3 X12 actuators simultaneously. So Xn represent their goal position. So we have X1, X2, X3, and N represent the motor ID number. Okay, so the code is here. So we have a theta that will be changed later, but the initial value is 0. Okay, and so we do this indefinitely forever. And the goal position of one motor is defined as the follows. So we have equation here. Okay, so we have sine something, right, plus 1. So sine something, some number here in the bracket, that sign of that number is always between -1 and +1, right? And this number +1, that over here, this number will be what? Will be between 0 and 2, right? And times 512, okay? So this goal position will always between what? Between 0 and 1023, right? Okay, so that's the purpose of this code. Okay, so for each motor, we have a different initial value. So that depends on the n here. So if n is equal to 1, we have some value here, okay, and n is equal to 1 actually, okay. Your initial value is over here. And if n equals to 2, it's over here, and 3 is over here. So what we do here is that we increase the theta by a small number, pi over 100 at a time, okay? So basically, we move these 3 arrows to the right, okay, gradually. Okay, so the motor position is controlled like doing up and down, up and down, up and down. And that's basically this example is doing. And I also create, the animation here to help you understand. So let me show you it again. So it's doing this, the moving the position gradually. Okay, and here are some details of how an instruction packet is defined for synchronized write. But I'm not going to explain them. I'll just leave this to you. And also we have an example right here. So just go through this example and you will have a better idea how to create a synchronized write instruction. And let me show you how the program actually works. So let's download the program to the CM510. And the program name is Synchronized. Okay. And as you can see here, okay, the motors are rotated to different positions at different speeds. Okay, and the screen shows the current position of the three motors. Okay, and this is this example. And now let's move back to the slides. Oh, before we leave this example, there's one more thing that I have to explain. So, in this example, we use a math function. Okay, so in this example is in the folder Synchronized. Okay, and in the main.c over here, okay, see here we use a math function sine. Okay, so in order to let the compiler understand that you use a sine function in the math library, you have to include that math library, okay, in your settings. So how do you do that? You right click on the Synchronized, okay, and you choose the property. Over here, and then you choose the C double plus builder and click setting. Okay, and here there's a library, see over there, right? Okay, and in default this is empty. Okay, so what you want to do is click plus and type 1 and type M over there. Okay, like that. So it is empty like this, and you click on that green cross button and type M here. Okay, and that's it. That's all you want to do. So when you compile the code, the compiler can understand, okay, this sine function is from the library, so the program can be compiled appropriately. Okay, now let's go back to slides and see the next example. Example 9, RC100 through ZigBee. In this example, we'll explain how to communicate with a device through ZigBee. And we will need a RC100 with a ZigBee 100. Okay, and also we need CM5 with ZigBee 110. And when we receive a command from RC100, the CM510 will do something. And in this example, that is to turn on an LED when you receive if a button on RC100 is pressed. Okay, and we know that ZigBee communicates with CM510 through UART. So we have to set up the port for UART communication appropriately. So how do we do that? So look in this table that communication control port is port D. So basically what you will need to do is to follow the code over here. Okay, so this is all about port D. Initialize that port communication for you. And this is what you will see in the example code later. And here we have some C functions for ZigBee communication. So we have this one for initialization, and this one to check if there is a data comes from the ZigBee device. And if there's one, we have a function to check what that data is, to read that data value in the communication package. So here is a table, okay, shows the RC100 data. Okay, so that means like if a button is pressed on RC100, there is a corresponding integer value. So this function gives you an integer value, and that integer value can be any combination of these values. Now let's see how this program works. Let me pull up the program in the Eclipse. The program is in the folder ZigBee RC100. And let's see the main.c over here. So in the beginning, we include the header files. And here we define the LED. And here is the section for ZigBee initialization. Okay? You have to initial the communication and also use this function ZigBee initialize and then enable the interrupt. Okay, and here is the main function, and this is the program runs this continuously. So first we check if data is received from ZigBee device. Okay, if it is received, it is equal to 1. Okay, and if it is equal to 1, something comes in, then we read what that is and store the data in this variable RCV data. Okay, and if a button 1 is pressed, then you turn on this LED. And if button 2 is pressed, then turn on this LED. And button 3 is pressed, turn on this LED. And that's the program. So let's see how it works. Now we want to download the program to the microcontroller. And the program is named ZigBee RC100. Okay, and I have a RC100 over here. Okay, and I turn it on. Okay, now if I press a button here, okay, a number button, the LED will be turned on. So this is the example. Okay, and next is practice time. So here are two practice. So first is to program a buzzer to give a warning sound when the IR sensor detects an object. So this is an easy one. And what you need to do is to combine the example that I gave you. And the second is to do a remote control smart car based on the provided example. Okay, the automatic smart car. I didn't talk about the automatic smart car, but I'm going to show you right now. So let me download that program. So the automatic smart car, the code is provided to you. Okay, and the program runs like this. Okay, let me pull the serial cable. So this is automatic smart car. Okay, and that's what this is what we just did with the Robotis. Okay, when the IR sensor detects something, it will stop. Okay, or go back, and this applies on the IR sensor on left hand side too. Okay, so if there is some obstacle in front, it will stop and moving back. And if there is some obstacle on left hand side, it will start to turn. Okay, otherwise it will keep moving forward. Okay, so this is the automatic smart car. Okay, moving pretty smooth. And I would like you to based on this program to write a program so that the smart car can also take command from ZigBee. So it can be a remote control smart car. Let me show you the code. Okay, so in the package that I provided, there is a folder, automatic smart car, over here. And let's see the main.c. So this is basically a combination of ZigBee RC100 and the Dynamixel control. And here we have enabled two ADC port. So this is ADC port 1 and this is ADC port 2. So port 1 is for the front sensor, and this is the ADC port 2 is for the left side sensor. Okay, and we determine the moving of the smart car based on the sensor reading. So if we detect obstacle in front, and we go backward, and if we detect obstacle in the left hand side, we turn right. Okay, and else if nothing is detected, we go forward. Okay, so what I would like you to do is to write a program based on the code that I provided to repeat the project 1. So basically, it's going to be a remote control smart car, but it also has the function of automatic obstacle avoidance. So this is the lecture for today, and I hope you enjoyed. Thank you.